just one out of it, 52 waves. And what do I mean by the inverse of that collision? I mean, not run it backwards. You can do it that way too, in a sense, but that, I'm talking about taking this molecule with this, about changing direction to all these arrows. Change the direction to all these arrows, down here. And allow them to collide in just this manner, and what happens? Now, coming in, V1 is coming in. It's moving the same way as before, but somewhere different in physical space. And it impacts molecule 2, which is moving the same way as it was before, but arranged differently in space, so they contact this plane. What that does is that throws this velocity into that one, this velocity into that one, and that just restores both of the simultaneous. Start running it backwards. Yeah, that thing about it a bit. So if we look at the forward reaction, that will that'll take a point out of this box and throw it into this box, and point out of this box, put it in this box, and the inverse reaction will just undo this. And that's a wave. That's one out of an infinitude of waves. Now, detailed balancing requires the probability of a forward reaction, a forward collision, to be the same as the probability of the inverse collision. And if you invoke that for every collision, you wind up with a stable distribution of velocity space. So, all right, detail balancing. Requires the rate of the forward collision, rate of inverse collision, and that's the key. So, rate of the forward collision what factors are going to influence that rate? They're going to be how many molecules are moving such that their points are in dV1, right? Suppose there were no points in dV1, then what's the rate of that collision? It's zero. If you don't have something moving that fast, you can't have that collision. It'll depend on the number of points in dV2 for the same reason. And it depends on the number of points in dV1 and the number of points in dV2, that how does it depend on both of them together? It depends on the product. If you double the points in dV1, you double the rate. If you double the points in dV2, you double the rate. If you double them both, you double it, you multiply by 4. Must depend on number in dV1 and number in dV2, or that the rate forward must be proportional to. Now we know how to write these. It's the number of molecules in the box. It's rho of V1, dV1. Number of molecules in the box, rho of V2, dV2. And similarly, for the inverse collision, what can we say? The rate inverse And the number in dv2 prime, and that's rho v1 prime times dv1 prime. And that's the number times rho v2 prime times dv2 prime. And rho forward equals rho inverse. That's detail balancing. You see, there are lots of other ways to point to move them out of those volume elements. But this is one specific way because it's highly detailed. But it could be any collision you can imagine if you apply this argument to it. So if that's required, then we just equate these two. And you can see when you equate them, what's going to happen to the number of molecules, it's going to cancel out. Right? On both sides, we put equals there. And we're going to have rho of V1, dV1 times rho of V2, dV2 is equal to rho V1 prime, dV1 prime, rho of V2 prime times dV2 prime. These equations are all in the notes that will be on, or the lecture will be online. No, and more. As a matter of fact, on the online lecture, you'll find this equation 8. Now, all right, we're interested in just the rho of these, not interested in dV's. Those are arbitrary, and they're infinitesimal, they're arbitrary. Clearly, the size of dV1 prime and dV2 prime, these volumes, depend on what sizes dV1 and dV2 were before. Does that make sense? All right. So I've just drawn little boxes here. But if you change the size of this one, it's going to change the size of these two over here. Change the size of that one's going to change the size. They've got to be related. And Maxwell showed in intuition and little geometry showed that dV1 times dV2 was equal to dV1 prime times dV2 prime. That Poisson number. Anyway, he showed that. So, equation 8 then becomes, and looks what happens. Here's dV1, here's dV2, here's dV1 prime, dV2 prime. dV1 doesn't cancel dV1 prime, dV2 doesn't cancel dV2 prime. The product dV1, dV2 cancels the product dV1 prime, dV2 prime. And equation 8 then becomes rho V1, rho V2 is equal to rho V1 prime times rho V2 prime. And that's my equation 11. We're going to do that because there are certain things when the collision takes place, there are certain things that are conserved. You know any of them? Kinds of collisions? These are elastic collisions. Know anything conserved in elastic collisions?
Momentum.
Say it to me.
Momentum.
Momentum, that's one. And anything else that's conserved? Yes. Absolutely, I love that. Kinetic energy. The kinetic energy is conserved. So a molecule may speed up, no, it has to go down. So this, what else do we know now? We know that the logarithm of the probability distribution, the points of velocity space is conserved. Therefore, the logarithm of rho of v is what we call summational invariant. Now, I don't know who's funding your education, and maybe your parents are contributing, know if they are. And when you go home, they like to hear that you've learned something worthwhile with the money they're spending. So when you're chatting around the supper table, if you talk summation invariant in the conversation, they'll say, yes, we got how money worth. That's not what we're doing. But that just means that the sum of those, the sum of that quantity is conserved on the course. What are others? Well, as I said, the momentum, mass times velocity, that's a vector quantity that's conserved, and kinetic energy, that's a scalar quantity that's conserved. We know it. Consider kinetic energy specifically. Therefore, for our forward collision, we have 1/2 m v1 squared. No arrow on this now. Plus 1/2 m v2 squared is equal to 1/2 m v1 prime squared plus 1/2 m v2 prime squared. Well, pretty clearly we can strike out the 1/2 m's and just get v1 squared plus v2 squared is equal to v1 prime squared plus v2 prime squared, and that's nothing more than equation 13. And your notes on the formal lecture. All right, here's a summation invariant, and here's a summation invariant, right? And we know about v1 squared and v2 squared. We know what those things mean. But we don't quite know what that is. But you have to be always clever at Janford Maxwell, which is a pretty big order, but you don't have to be that clever, because by this time any idiot can see that probably, here's our summation, probably the logarithm of rho of v is related to the square of the velocity, the square of the speed rate. And that's all it's involved in deducing this marvelous result we're going to get here momentarily. That's the magic right there. I'm impressed every time I see it. So, compare equations, what were they, 8 and the 11, I guess, 13, whatever, I don't remember. 11, 13. 11 and 13. Maxwell's, we say postulate, but it's really a guess. Is that everybody see how you can make that connection? Those two equations? Thank you. One does, and that's enough for me. I'd like for everybody to see that. Really good. This is really good stuff. Wow. Well, this is not so much for his guess was. That's pretty obvious. Here's what his guess. See, we want to know what is this. It's a function. What the hell is a function? So here's Maxwell's guess. So what are you going to guess? Well, let's see, function of v squared. Well, it could be v to the fourth power. So that's v squared squared. Or it could be the sine of v squared. It could be anything. So when you're at this juncture, playing the game of science, you're not quite sure what the answer is, what do? You first look at the simplest case, right? First look at the simplest one. And what's the simplest one? Simplest function that satisfies that condition is that the logarithm of rho of v is a linear proportion of v squared, or the logarithm of rho of v is equal to this cost, call it little a, and another constant, b times v squared. That's S. Now, for reasons that may or may not become apparent a little later, I'm going to keep A. These are A, little a, little b are constants. We don't know what they are, they're constants. But I'm going to give this one a different name. I'm going to give it minus beta. Well, hell, that's all right. We can call them any constants we want. Call one A, the other minus beta. If we do that, then the final result is the more appealing form. Right now it's just gibberish. Then we have the logarithm of rho of v is equal to a minus beta v squared. Or taking the anti-log, we have rho of v itself, which is what we didn't know when we sat down here this morning, is equal to e to the 8th power times e to the minus beta v squared. Oh. This is a constant, and beta is a constant. So let's just give this one another name. This constant we'll call just capital A, and then e minus beta v squared over v. Oh my God. That's equation 16. That is the Maxwell distribution of velocities. Notice there are no arrows in there, just v. So it's spherically symmetric, right? That depends on what direction velocity is. If you choose a speed, the distribution is uniform on a sphere with a radius equal that speed. That's good. That's Maxwell distribution. Let's rewrite this. Let's rewrite this as rho of v over a is equal to e to the minus the square root of beta times v squared. Because that's a pretty stupid thing to do, and it generally is. Other than we can write that as e to the minus x squared if we let x equal the square root of beta times cv. Now, why would I want to do that? So that I can show you this graph This is the maximum distribution. Here's rho of V over A, here's the square root of theta times the x. That's what I call x. So this is a reduced notation. This is the maximum distribution. And what is it? Whoa! It says that the most probable single velocity for a molecule in a harmonic gas is what? This is a probability distribution. If I say, what's the maximum probability? And you sure you know how to find the maximum on that curve. 0. Yeah, 0. And you say, well, hell, this is a kinetic theory. It's not a zero theory. Yeah, but there's lots more points away from that origin. Right? Lots more points. See, the volume all around the origin includes all of the points around the origin. The volume element out here at this speed includes a big sphere, lots of points. Well, anyhow, that's it. So what is it? It's 0 when we express this in reduced notation. If distribution is normalized to 1 here, and then it falls off very rapidly. Very rapidly. And that is so important. That's one of the most marvelous things discovery about our world. Is that molecules have higher speeds or higher velocities, lower probability. And I wrote, I think, in the introduction that our world consists of things that will burn and things that have been burned already, plus a burning source of oxygen. And the things that will burn wouldn't be here if they were already burned. We'd all be burned. We'd all be carbon dioxide and other nickel cruds. So why aren't they burning? That's because to get a reaction, combustion reaction going, you got to strike a match or something. Start it, have to ignite it. Once you get it going, make it sustain itself. Now, in nature, what starts those reactions? It's one real kick-ass molecule banging into another and with enough energy to overcome some activation barrier, and the reaction starts. And then if those things develop enough energy before it all quiets down, it may be a chain reaction. They continue. So, all right. But you got to have those real fast suckers to do that. You got to have enough of them to make this sustainable. And you come out here where the real fast ones are, and what's the probability? It's getting closer and closer to 0, right? That's why I call Maxwell's tail. We're here because of Maxwell's tail. The molecules on Maxwell's tail are the ones that can initiate reactions at the rate at which that happens is very low, and therefore we can have a space. All right. So, what's next? What is the distribution of scalar speeds? We have a distribution of velocities. It's symmetrical about the origin. It's spherically symmetrical. This line here, I drew that just on some line. You've got to have a line through the origin of this. I call this the x direction. This is the y direction, z direction, the other direction. You get that same shape. It's hard to draw in 3 dimensions. I wish I could. I've got an artist rendition of it here.